Two of the most advanced airliners ever built, the Boeing 787 Dreamliner and the Boeing 777, are suddenly being stripped of their aura of invincibility. These jets were supposed to be masterpieces, the kind of aircraft engineers point to and say, "This is what the future looks like." But in the last few months, something unsettling has happened. We've seen cockpit controls change numbers on their own. We've seen pilot seats jolt forward so violently that they sent airplanes plunging without warning. And we've seen safety notices that hint at the unthinkable. The tiny possibility of an engine separating from a wing if corrosion goes unnoticed. These aren't rumors. These are real safety directives, urgent ones, landing on airlines' desks from regulators who rarely use words like immediate or mandatory unless something is truly serious. So the big question becomes, what's actually going wrong? Who is responsible? And most importantly, are passengers still safe? Right now, thousands of flights a day rely on these aircraft. Families, business travelers, pilots, crews, everyone trusts that the tech on board works perfectly, but trust only holds if the engineering does. To understand why these warnings hit so hard, we need to go back to what made the Dreamliner and the 777 so revolutionary in the first place, and why that very brilliance created new kinds of fragility. Before the warnings, before the incidents, before the headlines, these two aircraft were legends, not because of luck, but because Boeing pushed aviation into new territory. The 787 Dreamliner, a radical break from the past. When the 787 was introduced, it wasn't just another plane. It was a reset button for wide-body design. Instead of aluminum, Boeing built most of the fuselage from carbon fiber composites, a material more common in Formula One cars than commercial airliners. Composites don't rust, they're lighter, and they flex differently under stress. That means better fuel efficiency, smoother rides, and longer-lasting parts. But there's a trade-off. Lighter materials also fail differently. Where aluminum dents, composites can hide internal damage. When moisture slips into the layers, it behaves in ways older aircraft never had to worry about. Then came the electrical revolution. The 787 replaced many traditional hydraulic systems with electrically driven architecture, like giving a plane a more digital, centralized nervous system. Fewer mechanical lines, more computers, sensors, and software. This new design delivered incredible benefits: lower fuel burn, simpler maintenance in theory, and a cockpit packed with next-generation avionics. But more software and fewer mechanical backups also mean, when something glitches, it can ripple across multiple systems at once. The Boeing 777, the old masterpiece showing its age. Then there's the 777, the opposite story. Where the 787 is the bold experiment, the 777 is the workhorse built to last. It has flown millions of hours and earned a reputation for toughness. Airlines love it because it just works. But today, many 777s are 15, 20, even 25 years old. In aviation, that's senior citizen territory. Aging aircraft develop predictable issues: corrosion, stress cracks, worn connectors, outdated components. Nothing shocking, but all requiring constant scrutiny. Just like an older car that needs more checks, even if it still runs beautifully. Here's the heart of the story. New tech brings new failure modes, while old tech brings wear-out problems. The 787's challenges often hide in software, electronics, and the complexity of composite materials. The 777's challenges, on the other hand, often hide in aging metal, seals, connectors, and decades-old hardware. And both jets share something else: a global supply chain. Boeing doesn't make most of the parts itself. Cockpit panels, actuators, oxygen systems, seats, all come from specialized vendors. When a supplier slips, the entire aircraft inherits the problem. This combination, cutting-edge systems, aging fleets, and outsourced components, sets the stage for the incidents that followed. Now, when you look at each of these issues on its own, it might seem like a small glitch, a minor defect, or something caught early. But aviation doesn't work that way. Tiny problems, the size of a loose connector or a kinked tube, can snowball when they interact with software, sensors, and human reaction. And that's exactly what we've seen. Let's walk through the key incidents that shook confidence in the 787 and 777. First, the MCP or autopilot knob glitch, when the plane chooses your altitude. Imagine you're a pilot dialing in 34,000 feet. You twist the knob, and suddenly the selected altitude jumps to a completely different number on its own. That's what crews started reporting. The issue traced back to the mode control panel, essentially the autopilot's command center, with a specific batch showing encoder and software interaction problems. Airlines found panels where the altitude selector could self-adjust, forcing pilots to double-check every change. For passengers, nothing dramatic happened, but pilots described the moment as, "Wait, did the airplane just change that by itself?" In aviation, that's a chilling question. The second incident is the pilot seat event, the LATAM plunge. The most dramatic event came from something almost laughably simple, a seat mechanism. On a LATAM 787, a pilot's seat suddenly slid forward with force. The movement slammed the pilot into the controls, sending the aircraft into a sudden nose-down motion. Passengers felt the drop instantly. Food trays flew. People hit the ceiling. Dozens were injured. All because a switch, normally used to adjust seat position, could activate at the wrong moment or fail internally. It's a reminder that in a cockpit full of computers and automation, sometimes the weakest point is a mechanical part right beneath the pilot. Third, kinked oxygen tubes, a hidden survival risk. During a depressurization emergency, oxygen masks are supposed to drop automatically. Except investigators found kinked oxygen tubes inside some 787 overhead units. A tiny bend in a plastic line, something a mechanic might not even notice, could block oxygen flow when passengers need it most. It's the kind of flaw that stays invisible until the worst possible moment. Fourth, misinstalled FPBs and moisture intrusion, corrosion that creeps. The flight path barriers, or FPBs, part of the structural lining inside the fuselage, were found misinstalled in certain aircraft. That mistake created gaps where moisture could seep in, get trapped, and quietly corrode metal beneath composite layers. Over time, corrosion leads to cracks. Cracks lead to pressure loss events. On a composite-heavy jet like the 787, moisture doesn't behave the same way as in aluminum, making this problem harder to detect and more dangerous when ignored. Fifth, ACMP wheel well fire risk, when missing seals become flames. Another issue came from the air-cooled motor pumps. Missing seals and lock nuts could cause the pump to overheat, especially inside the wheel well, a tight enclosed space next to the landing gear. An overheating pump in that environment doesn't just fail, it can ignite surrounding components. The FAA didn't take chances. They flagged the risk as urgent. Sixth, PW4000 engine failures, echoes of United 328. You might remember United Flight 328 when a 777 engine exploded and rained debris over a Colorado suburb. Those engines, the PW4000 series, face ongoing issues with turbine blade durability and inspection procedures. Metal fatigue can form microscopic cracks that grow over time, turning a single blade into a fragmentation grenade. Ultrasonic inspections were ordered fleet-wide to catch flaws before the next disaster. And seventh, water leaks into avionics, the faucet that nearly became a flight risk. And then there's the strangest one. Simple lavatory faucet leaks allowed water to drip into avionics bays where flight control modules live. Water and electronics mix about as well as fire and fuel. A small drip can short a circuit. A short can scramble a signal. A scrambled signal can confuse the aircraft's control logic, all because of a leaky sink. Why do these incidents matter? None of these issues caused a crash. But every one of them shows how interconnected modern aircraft are. A defect in a $40 seat switch can trigger the same chain reaction as a flaw in a $1 million avionics module. These incidents aren't random. They share a pattern, small faults revealing deeper systemic vulnerabilities. When investigators step back from individual incidents, a bigger picture comes into focus. Not one failure, not one bad part, but a network of vulnerabilities, scattered across hardware, software, manufacturing, maintenance, and oversight. Think of these incidents like cracks in a windshield. Each crack starts somewhere different, but they all hint at stress across the entire structure. Let's break down what the investigations uncovered. To start, let's talk about manufacturing defects. Those small errors that, well, sometimes slip through. Some of the problems actually began right where the aircraft was built. Things like misinstalled FPB panels, missing seals on ACMP pumps, or oxygen tubes kinked during assembly, none of these are catastrophic on their own. But honestly, they do reveal some gaps in quality control. Large jets aren't built in just one place. A single 787 or 777 comes from hundreds of subcontractors, each handling a tiny piece. If even one supplier slips up, even just a little, the defect can travel all the way into frontline operations. Then there's the design side. Composite fuselages don't really show damage the same way aluminum does. Electrical systems are supposed to reduce mechanical complexity, but they can actually concentrate risk in a few high-level components. And when software sits at the heart of everything, the line between a design choice and a design flaw can get pretty blurry. The MCP anomaly is a perfect example. It wasn't just a bad encoder. It was the interaction between a hardware tolerance issue, a software interpretation error, and a production batch with slightly off specs. Three small factors that together created one surprising failure mode. Now, let's look at software and electronics. Modern aircraft rely on integrated avionics, dozens of computers talking to each other all the time. So, a glitch isn't isolated, it spreads. Maybe it's a cockpit knob that misreads the pilot's input, a sensor that sends corrupted data, or a short circuit caused by a leaky faucet. In older jets, these issues would stay limited to just one system, but in the 787 and late model 777s, they ripple across multiple subsystems because everything shares data. It's kind of like the aviation version of a smart home. If the Wi-Fi router breaks, suddenly your lights, thermostat, and doorbell all stop working too. And then there are human factors, installation, maintenance, and just the everyday pressures. Pilots, mechanics, and line technicians are all extremely skilled. But they're still human. Sometimes seat switches get installed just slightly out of tolerance, or oxygen system tubing gets routed a bit too tight, or avionics panels are resecured improperly after a routine check. The more complex the aircraft, the easier it is for a small oversight to cause a major chain reaction later on. And with airlines pushing tight schedules, relying on outsourced maintenance, and facing cost pressures, mistakes become more likely, even with strict procedures in place. One of the quiet truths behind all of this is the supply chain. Boeing doesn't build the whole plane. They rely on companies like Honeywell, Collins, Spirit Aerosystems, Panasonic, Pratt and Whitney, and dozens more. Each one provides a critical part. But coordinating that ecosystem is its own challenge. A flaw in one supplier's batch can sneak past Boeing's acceptance tests. A software module written by one vendor may not perfectly fit another vendor's hardware. And a part that technically passes inspection can still behave unpredictably in real-world conditions. The Swiss cheese model explains this well. Every layer, design, manufacturing, testing, installation, operation, has tiny holes. An incident occurs when all the holes line up, and in several of these cases, they did. So, here's the big picture. Investigators concluded that the failures weren't just random, they were systemic. Not because one system was broken, but because, well, many small weaknesses existed at the same time. That's exactly why regulators stepped in so aggressively. and why the next phase, the fixes, became so expensive, so urgent, and honestly, so unavoidable. Once regulators saw the pattern, small faults stacking into big risks, they didn't wait around. They issued airworthiness directives, or ADs, which are basically command-level instructions. Fix this now, or the aircraft doesn't fly. It's aviation's version of a mandatory recall, except the stakes aren't just a stalled engine on a highway, they're lives at 35,000 feet. Let's break down what these fixes look like, how much they cost, and why they matter. First up, MCP replacements, a costly swap for a critical brain. The mode control panel issues didn't get a software patch. Regulators wanted outright replacement. For the U.S. fleet alone, about 165 Dreamliners needed new MCP units. The estimated cost per aircraft? Roughly $405,000. For airlines already squeezed by tight margins, that's a punishing bill. And this is just one directive. Next, pilot seat switch inspections, a simple fix with some pretty serious stakes. After the LATAM incident, the FAA demanded immediate checks and reconfiguration of pilot seat switches and wiring. This isn't a high-cost repair, but it's definitely labor-intensive. Mechanics have to inspect the switch wiring, secure or replace mounting hardware, test travel limits, and verify that no unintended activation is possible. Every hour an aircraft sits in a hangar is lost revenue. Multiply that across dozens of planes, and the cost rises fast. Then there's PSU and oxygen system work, finding those invisible problems. Kinked oxygen tubes triggered directives that require airlines to open passenger service units, those overhead compartments with the masks. Technicians must remove each unit, check tubing for bends, replace lines if necessary, and then reinstall and retest dozens per aircraft. It's slow, detailed, and absolutely critical. You just can't gamble with emergency oxygen. Fixing misinstalled FPB panels isn't just about tightening screws. Mechanics have to open interior structures, inspect for trapped moisture, check for corrosion and hidden layers, reseal or reinstall panels, and repair any discovered damage. On composite aircraft like the 787, this inspection requires specialized tools and often longer downtime, which, of course, means more cost. Some 777s and 787s require new air-cooled motor pumps with proper seals and lock nuts. The directive includes testing all related components in the wheel well, an area that's cramped, hot, and just tough to access. It's a classic high-labor, moderate-cost fix that disrupts schedules more than budgets. Fan blade inspection on PW4000 engines is one of the most expensive fixes. Ultrasonic testing requires engine removal or partial disassembly, specialized equipment, certified inspectors, and multi-day downtime. And if even one blade shows fatigue signs, the replacement cost can hit 6 figures per blade. Finally, the remedy for water leaks into avionics involves sealing or replacing affected faucet assemblies, inspecting wiring and avionics trays, and applying redesigned components where needed. It might seem trivial, but any cleanup that involves electronics becomes time-intensive and, costly. Short-term versus long-term fixes. Well, some repairs, like swapping MCP units, are pretty straightforward hardware replacements. But others, like corrosion checks or engine inspections, they really hint at deeper systemic changes. Things like better supplier oversight, redesigned components, and new quality control checks. Airlines end up paying not only for the parts themselves, but also for aircraft downtime, scheduling changes, canceled or delayed flights, mechanic labor, and even certification paperwork. And sure, Boeing often covers some costs under warranty or through settlements, but honestly, airlines still carry a heavy burden. The safety equation, ADs aren't punishments. They're actually part of the aviation safety net. They're designed to catch issues early before they can turn into accidents. But, the sheer number and variety of ADs hitting the 787 and 777 fleets really raises the question. Are we just patching symptoms, or are we actually addressing the root causes? That's where accountability and reputation come into focus. And honestly, it's why the next section matters so much. Every airworthiness directive, every headline, every technical bulletin, it all adds weight to a larger question. Who is responsible for all this, and what does it mean for Boeing's future? Because while each incident might involve a supplier, or a mechanic, or even a specific hardware batch, the public sees only one name on the side of the airplane. For most passengers, Boeing isn't just an engineering company. It's, a symbol of safety, a brand that stands for millions of safe flights every single year. So, when multiple airworthiness directives, or ADs, hit two of Boeing's most iconic aircraft, the 787 and the 777, it really chips away at that trust. Even if no crash actually occurred, and even if the risks were caught early, people tend to remember the dramatic moments, not the technical explanations. Cockpit controls acting strangely, a plane plunging during cruise, an engine exploding mid-air, or oxygen masks maybe failing to deliver air. Even if each of these problems is rare, the pattern kind of creates fear. And honestly, fear is really hard for any company to fight. Historically, Boeing and the FAA had a close working relationship. But after the 737 MAX crisis, that relationship changed. Now, the FAA demands more data, approves fewer internal shortcuts, and issues ADs faster and more forcefully than before. Other regulators, like those in Europe, Canada, and Japan, are watching these moves closely. If they see Boeing's U.S. aircraft getting repeated directives, they start asking tougher questions too. In other words, Boeing is under a brighter spotlight than ever. Airlines really depend on the 787s and 777s as the backbone of their long-haul fleets. So, every airworthiness directive forces some pretty tough decisions. Do you ground the aircraft for inspections? Do you delay or cancel flights? Or maybe you have to reassign older, less efficient planes? Sometimes you just have to absorb those multi-million-dollar fixed costs. And honestly, there's also a psychological burden. When mechanics spend their days chasing one safety issue after another, it really raises stress. When pilots hear about anomalies from other crews, it raises concern. And when cabin crew see passengers shaken after incidents, it raises the stakes for everyone. Behind every headline, there's a workforce working hard to keep the system running safely. Now, Boeing isn't the only player here. Parts come from Honeywell, Spirit AeroSystems, Pratt & Whitney, Collins Aerospace, and, honestly, dozens more. A defect at any point in this chain becomes a Boeing problem instantly. This is the challenge of modern aviation manufacturing. Quality control is only as strong as the weakest supplier. That means Boeing faces not just its own internal issues, but also the shortcomings of partners spread across the globe. Even before these incidents, Boeing was already facing some pretty severe pressured production slowdowns, delayed deliveries, competitive pressure from Airbus, and rising costs across its supply chain. Layer on top of that multiple airworthiness directives hitting two flagship wide-body programs, and, well, the market reaction is pretty predictable. More scrutiny, more skepticism, more volatility. Airlines negotiating new purchases can use incidents as leverage. Governments ordering aircraft start asking harder questions. Investors get nervous. Reputation isn't just an image, it's a currency. So who's to blame? The tough answer is everyone and no one. Boeing designs and integrates the aircraft. Suppliers build countless parts. Regulators enforce safety. Airlines maintain fleets with varying standards. Mechanics and engineers implement fixes. Software decisions impact hardware performance. When things go wrong, it's rarely just one smoking gun. It's the system, the culture, and the complexity of modern aviation, all colliding. But the public doesn't really see that nuance. To them, the question is simple. Is Boeing safe? And that brings us to the final section. What passengers should take away, and what this all means for anyone stepping onto a 787 or 777 tomorrow. So what does all of this mean for the millions of people who step onto a Boeing 777 or 787 every single week? Here's the truth, and honestly, it's less dramatic but far more important than the headlines. Aviation is still the safest form of transportation on Earth. Every day, these aircraft complete thousands of flights without a single issue. Pilots, engineers, and regulators live by the rule that one problem is one too many, which is why even small glitches trigger industry-wide responses. The recent warnings don't mean the Dreamliner or the 777 are unsafe. They mean the safety system is working exactly as designed. But this moment also exposes something deeper. When technology becomes incredibly advanced, it also becomes incredibly sensitive. A miscalibrated sensor, a corroded pulley, a software update that talks to hardware in a slightly different way. Tiny things can create big consequences. And that's why transparency matters. That's why accountability matters. That's why Boeing, after years of criticism, can no longer afford secrecy, shortcuts, or silence. Not when trust is the currency that keeps commercial aviation alive. If there's a silver lining, it's this. Every directive, every investigation, every fix is another layer of protection added to the aircraft millions depend on. Aviation evolves through lessons, sometimes uncomfortable ones, but always with one goal: make tomorrow's flight safer than today's. Because at 35,000 feet, there is no room for ego, no room for denial, only engineering, honesty, and constant improvement. And right now, the industry is being reminded of that truth in the loudest way possible. The sky isn't falling, but the warning lights are blinking, and everyone finally is paying attention.